Lesson 11, Addition of Fractions and Inscribed Angles. First of all, let's deal with addition of fractions. Let's recall the denominator-numerator rule, which says if I start with a fraction, the denominator and the numerator of a fraction may be multiplied by the same non-zero quantity without changing the value of the fraction. So I'm multiplying by c over c, the same non-zero quantity. Since c over c equals 1, this makes sense because whenever I multiply any number by 1, the answer is the original number. We're going to apply this rule when we add some more difficult fractions here. So a three-step procedure can be used to add fractions whose denominators are different. As we see, our common denominator will need to be, first of all, look at your constants. Okay, I have a 3 that appears in one of the denominators. Next, in that first denominator, I have a b. So I need to look in my other denominators and find the highest power of b that appears. Just at the first power, so we're good. Okay, move to the next one. I already have a single power of b. That's already covered. And then I have a z. I want to look at all of my denominators and find the highest power of z that's present, which would be 4. Therefore, my common denominator is 3bz to the 4th. As it turns out, what would we need to multiply 3b by to get 3bz to the 4th? We would need to multiply by z to the 4th. So we need to apply that numerator-denominator rule. Whatever we multiply to the denominator, we must also multiply in the numerator. All right, on the next denominator, bz to the 3rd, what would I need to multiply bz to the 3rd by to make it look exactly like our common denominator? We would need to multiply by 3, and then taking a look at the z's, I already have z to the 3rd power. I would need one more power of z to make z to the 4th. And apply your denominator-numerator rule. What you multiply in the denominator, you must also multiply in the numerator. So what we're doing here is we're multiplying by that funny form of 1, is what I like to call it. Okay, it's actually the number 1 we're multiplying by. It's just a funny form of 1. Okay, last denominator, we need to multiply just by 3. So top and bottom times 3. Now we want to examine our denominators. Okay, and notice we have 3bz to the 4th. Yep, 3bz to the 4th. Add those together, 3bz to the 4th. Now that I have a common denominator, I'm allowed to add together my numerators. So let's simplify my numerators. The first one, mz to the 4th. The sign stays the same in between the first and second numerators. Multiplying this together, let's put our constant first, 3, and let's put these in numerical order. Alphabetical order, excuse me. 3akz. All right, the sign minus stays the same in between the two fractions, and we're on that last numerator here. Y times 3, let's put the constant first, and then the variable. And we have our answer. Let's do one more. Example 2, add z over b minus k plus 2mn all over a b to the 3rd. This second number here does not have a denominator written, therefore we assume it to be a 1. All right, common denominator. What's that going to be? All right, so taking a look here, I know I have a b times a 1 times an ab cubed. Okay, So A is the highest power of A that appears in all three denominators. B is to the third. That's the highest power of B that appears in all three denominators. Therefore, my common denominator, let's write that at the bottom here over a big fraction bar. And let's set up, what do we need to multiply top and bottom by? What's our funny form of 1? We need the B to look just like AB cubed. So we would multiply times AB squared. AB squared also goes in the numerator. Okay, next up, well, we have a 1 in our second denominator there, so we're going to need to multiply that by AB cubed, the entire common denominator, top and bottom, numerator and denominator. All right, this last denominator, that is not going to need any work, right? It's already the common denominator, so we do not need to multiply at all. Okay, so we know when we have a common denominator in our fractions, we write a new fraction, okay, with the common denominator at the bottom, and then we are going to add together or sum up our numerators. So here we go. First one, z times ab squared. Let's put them in alphabetical order. A, b squared, z. Now the order really doesn't matter, but if we're checking our answers in the back of the book, or for ease of grading when we're grading together in class, okay, it might be nice if we have them in alphabetical order. Back of the book is always going to put them in alphabetical order. All right, and then we have minus k times ab cubed. So that's going to be the a comes first, then the b cubed, then the k. And then this last one here, we don't need to change that at all. It stays as 2mn, and we have our answer. All right, folks, it's time to get out our formula sheets. And you can put whatever number you're on the left column. And this is from lesson 11. We have some circle definitions. So tangent lines, okay? When we have two tangent lines or tangent segments, tangent to the same circle, they intersect outside of the circle, the tangent segments are equal. Okay, therefore x equals y. Some of you guys might have already put this in your formula sheet from the last lesson, and if so, I guess we'll just move on to the next one. All right, let's talk about the central angle. This is what we call the central angle here. It comes off the center of the circle, okay, and it's inside the circle, okay? So the rule is, if we're looking at the measurement outside, so this would be called the arc measure, okay? So not the arc length, not the arc length. Okay, that was a fraction of the circumference. We're talking about the arc measure in degrees now. So 360 degrees total. Okay, the degrees of the arc measure is going to be the same as the central angle. So if this is 20 degrees central angle, then the arc measure would be 20 degrees as well. Okay, we call this the intercepted arc. Where is it intercepted? Well, if you start at the center and you draw out each radius, okay, that point at which it intercepts the circumference on both rays, okay, that region in between, that's called the intercepted arc. Okay, the intercepted arc measure is the same as the central angle, always. Let's look at a different type of an angle. This is called the inscribed angle. Okay, in meaning in, scribed means written. So this is an angle that's written inside of the circle. It has its vertex on the circle or on the circumference. Okay, so here's the vertex. Okay, and then the rays that come out of the vertex also intercept an arc. So this intercepted arc has a relationship. It's different than the central angle. Central angle, the intercepted arc is the same. The inscribed angle, the intercepted arc is double. Double the inscribed angle. Where's the angle? Here's the angle. Remember, the vertex is on the circle. So here's the angle. If this angle is 20 degrees, go ahead and double it. The intercepted arc measure would be 40. Okay. So central angle, same. Inscribed angle, double. Okay, and the last thing we want to write down, I don't know if you have this already in your formula sheet, but you should have this somewhere. Circle sum, 360 degrees. Similar to the triangle sum being 180 degrees, sometimes we're going to use this as a reason when we justify for solving angles. Okay, so the sum of the degrees of a circle, always 360. So we're going to abbreviate. Let's talk about how we're going to abbreviate these. Circle sum, if you use that, CS. Let's go back. Inscribed angle, IA. Central angle, we already have CA, don't we? A couple times. So we had corresponding angles and we had complementary angles. So this one we're going to go like this. Cent A, central angle. Okay, that top one, do we need to justify here? We do not need to justify because this has to do with line segments. We only justify when we are solving for angles. Central angle, the inscribed angle, and circle sum. So with that, let's do an example. Example 3, find x and y. So let's find x first. So we see x is written in parentheses on the outside of this circle. So let's just break this down. What does that mean? Up here at the top, so if you have an angle measurement written outside of the circle, what that is going to refer to is you're going to look left and right to where any of the rays inside cut off a part of the circumference. Okay, so 4x plus 20 refers to this region here, okay, this arc right here. And so I'm gonna erase that, okay, and right on the outside. Okay, so that's that region there. This one here, 5x plus 80, well, look to the left and the right, or top and bottom. Look both ways, okay, look both ways. So that's going to be this intercepted arc right here. Okay. And then y is, well, look both ways. Y is going to be this remaining arc here. All right, so to find x, what we need to do is add up all of the arcs all the way around our circle. So we have 4x plus 20, and we have our blue arc plus 5x plus 80, and we have our green arc plus y. Okay, if I add those all up, what are they going to equal? 360 degrees. Okay, so that's circle sum. All right, problem here is we have some x's and we have a y. Okay, so we can't solve this yet. We can't solve an equation with two variables. So let's go ahead and find y first. So lo and behold, what we have here is we have an inscribed angle. So if the angle is 40, then the arc is double. Okay, so we're going to say y is double the angle. And we need to justify with a reason. Our reason is inscribed angle. Okay, so now that we have 80, okay, we can substitute right here. Y is 80. All right, let's go ahead and add up all of our x's. We have 9x. Add up our constants. So it looks like we have 180 equals 360, and we have a nice algebra problem to solve here. Okay, so subtract 180 from each side. Divide both sides by 9. And x is going to equal 20. Okay, so x equals 20 by circle sum. That's our justification there. And y is 80 by inscribed angles. All right, guys, I'm going to help you set up number 7 from problem set 11. There's a couple ways you can approach this. But what I notice here is I've got an inscribed angle. Okay, so once I find x, actually this is not an inscribed angle. X is a central angle. It's going to be the same as P, correct? The inscribed angle is right here. So inscribed angle has a vertex on the circle. So this angle 32, if I trace the rays out from the vertex until I get to the edge of the circle, I get P. So remember, our relationship is double. Okay, so the arc is double the angle. So if the angle is 32, we're going to double that and get P is 64. Okay, so P is 64 by inscribed angle. Okay, great. So let's kind of work backwards. Look at the purple writing. Okay, this angle here, that's a central angle because its vertex is at the center of the circle. Therefore, that's going to be the same measure as its intercepted arc. Okay. So we already know that P arc is 64 degrees. So x is also going to be 64 degrees. Okay, so let's write x is 64 by central angle. Okay, and then we hop over here. We have a straight angle, supplementary angles. So we're going to find y. It's going to be the difference between 180 and 64. So y is going to be what? Y is 116. Supplementary angles. So let's write that in. 116. And lastly, we have, notice here, these two marks here, these are radii of the same circle, therefore they're the same. Looks like we have an isosceles triangle. So my base angles of the isosceles triangle are going to be the same. So angle Z is 32 by isosceles triangle. And there you go.